Hello, ladies and gentlemen. Welcome to another exciting edition of HL Chemistry Flipped Classroom. This is Mr. Los. It's time to get going, folks. It's time to do this. It's time to get your swag on. It's time to put those thinking caps on. It's time to get ready to rock and roll. Let's go for it. What we are going to be talking about today is error and measurement uncertainty. Okay, we're scientists. Our job is to try to get at the truth of the universe, and we try to do experiments to help us achieve that goal. But there's going to be some things that are standing in our way. There's going to be some problems we're going to face in our experimentation. There's going to be some error that's going to pop up. There's going to be some problems, and that's what we're going to talk about, is some of these types of errors and some of the things that are going to stand in our way of getting at the truth. So when we do an experiment, more than likely, we're going to have to use measuring devices of some kind. And the very act of using measuring devices causes some problems. We call it random uncertainty or random error. I like the word uncertainty a little bit better. You might hear it called random error even by me, but I'm going to try to refer to it as random uncertainty. So basically, as we've probably talked about in class, if we haven't before, we will. There's limitations in measuring devices. They are not perfect. No matter what you do, there's going to be some flaws in them. And it's absolutely unavoidable that some amount of random uncertainty is going to pop up in any experiment that we do. You can't avoid it. You can reduce it by getting a better measuring device. There's always, at least in theory, a more precise measuring device that you could use. You could also repeat trials. That's one of the classic parts of experimentation, is repeating trials several times to get a better value. So one of the hallmarks and one of the things that we notice about random uncertainty is it's going to cause us to get values in a random fashion above and below the expected, the so-called true value. So, let's just say, for instance, the true value, the truth, is 5.00. That's the value that we're trying to arrive at. And we're doing some measurements. We might see when we do these measurements, we get values like 4.90, 5.10, or even 5. So notice that these values are hovering above and below this true value of 5. So this is the sort of thing that we see doing random uncertainty. And we could get a more precise measuring device that might lessen this variance a little bit. Or we could do more trials and average them, for instance. In fact, if these were 3 trials that we performed, if we average all 3 of them, it would in fact average to 5. Now, one thing, and one reason I in fact don't like the word error, I like the word random uncertainty better than random error, is a lot of times people think this is caused by using the measuring device wrong. Like this little guy here trying to use his tape measure and having a bit of trouble with it. Random uncertainty is not about using the measuring device incorrectly. What I'm saying is, even using a measuring device perfectly and perfectly correctly, there is still random uncertainty because measuring devices are not perfect. And the amount of uncertainty just depends upon the measuring device, okay? Now, of course, you can screw up making the measurement and make it even worse, but that's a different issue. That's not really what we're talking about here. So, depending on how precise the measuring device is, we may have talked about these in class, but we will report data in this class. When we report data, we'll report it with confidence intervals, which these basically show how precise the measuring device is. For instance, the electronic balances in our room, when you weigh something on those electronic balances, the balance can only determine the mass to within 0.01 grams. That's its confidence interval. So anything you weigh on that balance, it might be 0.01 grams heavier, it might be 0.01 grams lighter. That's the absolute best that measuring device can do. So we would report the value. Let's say it's 5.00 grams. Using that electronic balance, we'd report that as 5.00 plus or minus 0.01 grams. Perhaps in a certain kind of graduated cylinder. Again, keep using this number 5. Maybe we're trying to measure 5 milliliters. Well, in this particular graduated cylinder, that graduated cylinder is only capable, even when using it perfectly, it's only capable of determining the volume to within 0.1 milliliter. So we'd have 5 milliliters plus or minus 0.1. Now we could maybe find a more precise electronic balance, a more precise graduated cylinder, make these confidence intervals smaller, but they will always be there. There will always be some uncertainty in any measurement. Even the theoretical best electronic balance in the world, whatever that is, has a certain amount of uncertainty to it. So that's basically random uncertainty. It's the uncertainty that comes from using any measuring device, an unavoidable aspect of using any measuring device, and influences data in both directions. Now, we're going to talk about another type of error that's not always present in every single experiment. It often is, but systematic error is an inherent flaw in experimental method that skews data in one direction only. This is very important. Whereas random error skews us in both directions, systematic error is going to skew us in one direction. And it might be above the true value, it might be below the true value. For instance, again, this mythical correct value we're talking about, true value of 5.00. Say we're doing an experiment, we do 3 trials. We get 5.70, 5.60, 5.50. So notice a couple things. First of all, this is what I mean by one direction only. All 3 of these values are above the expected value of 5. That wasn't true in our last example of random error. But also notice that these values aren't exactly the same. So systematic and random error can exist at the same time. We're seeing variation in our data due to random error or random uncertainty, but all 3 of them are above the expected value due to some type of systematic error. The systematic error is an inherent flaw. Inherent means it's a part of something, or it's just part of the way you're doing something causes a problem. It could be a mistake in the way you've designed your experiment, or it might be just part of the nature of doing a certain type of experiment that there's always going to be systematic error to it. So let me give you some examples here. The simplest example I can think of is, suppose you're doing an experiment, you're weighing something several times, and there's something wrong, the balance is broken, it's miscalibrated, it doesn't work, and every time you put something on there, it measures it 0.5 too high, 0.5 grams, 0.50 grams too high. So hopefully you can see that if I do an experiment with this electronic balance, I am always going to be measuring values that are higher than they're supposed to be. In fact, 0.5 grams too high. So that's an example of systematic error. It's the device I'm using is flawed, so I'm always going to get values that are too big. And now you could correct for this if you knew this was happening, or you realized, oh, hey, this is measuring 0.5 grams too high. You could actually correct for it. You could subtract 0.5 grams from everything you've done, and you would have eliminated that systematic error. So that's something that happens with systematic error as well. It is possible to eliminate it or greatly reduce it, where you can really only reduce random error. You can't eliminate random error or uncertainty. Let me give you another, for instance. So let's say you're doing a reaction, you're timing how long it takes to do this reaction. So there's a very famous reaction called the iodine clock reaction, where you're going to see, I'm going to show you a video of it in a second, some solutions are mixed and they turn from clear to sort of a dark blue purple type color. Let me pop that video up. So again, supposing this is our experiment here, we've got a magnetic stirrer there that's stirring a solution around. We're pouring 2 solutions together. We start the stopwatch. Now we're going to stop the stopwatch when this color change happens. So imagine this is you. You're holding the stopwatch in your hand. You're just waiting. You're watching. You're waiting for this color change to happen. And you've got your finger on the timer, and boom, there it goes. So you stop the timer. The thing is, though, you have a certain amount of reaction time that's going to take place. No matter how good you think you are at Call of Duty or whatever you think you're really good at, everyone has a certain amount of reaction time. There's several things that need to happen for you to stop the timer. You need to see the color change take place. That information needs to go in your brain. That information needs to travel down nerves to your fingers. Your fingers need to press the button. None of this happens instantaneously. There's a certain delay that's there. And so therefore, if you think about it, you are always going to record times that are at least a little bit longer than how long the reaction actually took. In other words, the time you write down, the time that's in your stopwatch, it's always going to be just at least slightly longer than it actually took to make the color change, depending on how good your reaction time is. So by the very way you're doing this experiment, there's always going to be a delay there, and you're always going to record values that are too large, larger than they should be. So that's an example of systematic error. Now, of course, there's also random error in the measuring device itself. So these happen at the same time. But let me give you another example. This one's a little bit kind of harder to understand, I think. But suppose you're doing an experiment and your goal is take the temperature of a reaction mixture before the reaction and after the reaction. And the question is, how much does the temperature change? Suppose that's the experiment. Now let me pop up another video here. So this is a very simple experiment. There's just some vinegar in that beaker, pouring some baking soda in it. Classic experiment. Note the temperature is 19.0, I think, at the beginning of the experiment. And it's dropping, dropping, dropping. And it appears to be decreasing as the experiment goes on. So we noticed the temperature dropped during that experiment. It went from, let's say, 19 to 16, something like that, 16 and change. The temperature went down by about 3 degrees. Now there's some systematic error in this experiment for this reason. They did this experiment in a glass beaker, and what's going to happen is heat energy is going to move into the beaker. In other words, since the temperature of the beaker is dropping, heat energy from the room is also going to come into the beaker, and it's going to counteract that temperature change a little bit. So actually, the temperature is changing less than it would if, for instance, let's say we did this reaction in a styrofoam cup. We mix those solutions in the styrofoam cup. Now the styrofoam insulates things, right? It stops heat energy from going in either direction, so that sort of blocks some of the heat energy from the room. Now the temperature would probably drop more because that heat energy from the room is not entering into the beaker. It's not interfering as much because we've sort of isolated the reaction mixture. So in that case, we're actually seeing a lesser temperature change than we should. So our values that we're recording are always below what they should be. And I know some of this stuff can be hard to wrap your brain around, including what I'm just saying about the temperature changes, but it's really important. And we've already talked about this third bullet. It's really important when you think about systematic error. You should also at the same time be thinking about, is this error, is this piece of uncertainty, is it making values above what they're supposed to be or below what they're supposed to be? So this one, we're measuring values that are higher than they should be because the balance is measuring too high. Here, again, we're also timing the reaction. The reaction is, we're recording values that are a little bit longer than the actual temperature, than the actual time because of our reaction time. Here, if we had done this in a better insulated container, we'd see a greater temperature change. So we're recording values that are less than the expected temperature change in the third bullet. And we're going to do lots of practice with systematic error, and it's going to be a theme throughout the year. And I'm not saying it's easy, but it's something we're going to practice with and be thinking about a lot as the year goes on. Okay, so another thing to talk about is absolute and relative uncertainty. Absolute uncertainty is the actual value of the uncertainty. For instance, maybe on a big graduated cylinder, the uncertainty is 5 milliliters, plus or minus 5 milliliters. That's the absolute uncertainty. It's 5. Relative uncertainty is expressing the uncertainty as a percentage or some sort of fraction of the whole. So it's a relative thing. It's not an absolute thing. For instance, 100 milliliters plus or minus 5%, 10 milliliters plus or minus 5%. This is a relative uncertainty. The actual amount of this uncertainty is relative to how much you're measuring. In 100 milliliters, a 5% uncertainty would represent a range of 5 milliliters because 5 is 5% of 100. But same relative uncertainty on a 10 milliliter measurement, 5% of 10 milliliters is 0.5. So relative is just expressing something as a fraction of a whole rather than the absolute, which is just sort of the raw number. And in different circumstances, both of these might be useful or important. So you can convert a absolute uncertainty to a relative uncertainty hopefully very easily if you understand anything at all about percentages and how they work. So for instance, 5.5 milliliters plus or minus 0.2. That 0.2 is an absolute uncertainty. It's 0.2 milliliters. That's what it is. Very black and white. I could find the percentage, so my total measurement is 5.5 and it's 0.2. So 0.2 is 3.6% of 5.5. So that is a 3.6% relative uncertainty, or because this is 1 sig fig, let's round this to 1 sig fig. That's a 4% relative uncertainty. So we might, in different circumstances, express this certainty in two different ways. 5.5 plus or minus 0.2, 5.5 plus or minus 4%. The same thing, basically, within rounding error. It's the same general idea expressed in two different ways. Absolute and relative. It doesn't say relative next to this one, but that one's relative. You could also go the other way. You could turn a relative uncertainty to a absolute uncertainty, and again, it's relatively easy if you understand how percentages work. So I've got a relative uncertainty of 1.55 plus or minus 1%. So I could change that to an absolute if I just find 1% of 1.55. The easiest way to do that, or what I usually do, is I change this to a decimal by dividing it by 100. So that's the decimal form of 1%, and you just multiply the total value times the decimal. It's about 0.0155, but again, we're going to express this as one significant figure. So 1.55 plus or minus 1% is about the same, that's a relative, as 1.55 plus or minus 0.02. So that's the difference between relative and absolute uncertainty and how to convert between the two. So something that's good to note about absolute and relative uncertainty is that if you use the same measuring device, as you measure different amounts, your absolute uncertainty will stay the same, but your relative uncertainty will change. So as it says here, using a smaller amount, well, let's take a look at the example, for instance. Suppose I'm using a graduated cylinder and I'm measuring at 10 milliliters, and this graduated cylinder its uncertainty is 0.1. So that is my absolute uncertainty, it's 0.1. I could figure out what percent it is. That is a 1%, 0.1 is 1% of 10 milliliters, so that is a 1% relative uncertainty. Now I could use that exact same graduated cylinder, except this time I use it to measure 5 milliliters, and it's the same graduated cylinder, so its uncertainty is the same, but this value is less. So now 0.1 is 2% of 5. So even though I'm using the same measuring device, my absolute uncertainty is the same, my relative uncertainty actually doubles when I measure the smaller amount. It doubles in this case. So I know right now you're thinking, this is a party. We're having lots of fun. And, you're right. But bear with me here, because now we really need to try to put this all together and go to the next step. We're going to talk about propagation of error or uncertainty. As we've discussed, when you're doing an experiment, you're measuring things. No matter how precise your measuring devices are, there's always going to be some degree of uncertainty in that. But what you'll very often do in science experiments is you will take those values that you measured, and then we will do calculations with those values. Your uncertainty will always, especially your relative uncertainty, will always increase with each calculation that you do. Your uncertainty is going to go up. In other words, how well you know the number is going to increase with each calculation. This is called error propagation, or propagation of uncertainty, if you will, but it's because the uncertainty propagates. Pretty sure that's spelled wrong. Propagates meaning to propagate is to spread through something. So you start up with this measurement that has some uncertainty to it. That uncertainty spreads throughout everything else that you do with that number. And it is going to increase the uncertainty with each subsequent step. So let's consider this. Suppose we have a mass and a volume here. Suppose we're trying to find the density. So we've taken these things. There's uncertainty in the measurement. So there's uncertainty in both these measurements, both in the mass and in the volume. Density is mass divided by volume. So suppose I'm just trying to find the density using these two numbers. So what you're used to and what you've done in other science classes is you just divide them. Density is mass over volume, so we divide the two out. We get 9.08. The unit is grams per milliliter. But what you're not taking into account when you do that is the fact that we don't really know that this number is 3.1, 3.25, because it could either be 0.01 gram bigger than that or 0.01 grams smaller than that. Same with this volume. This volume could be 0.01 grams, 0.1 milliliters, I mean, larger than this or smaller than this. So let's take one extreme case. Let's say that this value, in actuality, the true mass is 0.1 gram above this. And this is actually 0.1 milliliter below this, which both are possible. So in that case, if those are the values, then the density is 9.11 grams per milliliter, or 0.03 grams per milliliter above what we got here. The other possibility is this could be 3.1, 3.24, because again, we have this uncertainty range, so this might be 3.1, 3.24, and this could be 34.6. If I use those values, which are possible, given the nature of these measuring devices, these values might be correct, then I end up getting 0.05. So notice I did it without, I just straight up divided numbers. I got 9.08. I did one extreme case, I got 9.11. I did another extreme case, 9.05. So actually, my density is 9.08 plus or minus 0.03 gram per milliliter. That is a greater uncertainty, relative and absolute, actually. Well, it's not a greater, it's a greater relative uncertainty than anything in here. And go ahead and check my math on that if you want to. But this is as a relative uncertainty is greater than either one of these. So that's what happens with error propagation, is your error, your relative error especially, will go up. There is a way to figure out how much your error is or what error propagation is doing to your values. There's kind of a shortcut way that we're going to use. When adding or when subtracting two measurements, so there's different rules depending if you're adding and subtracting or if you're multiplying and dividing. When adding or subtracting two measurements, you should add them or subtract them normally, round for sig figs, and add absolute uncertainties. So whether you're adding or subtracting, you will always add absolute uncertainties. And then whenever you're doing this, your reported values, or the value you actually write down, should have the same precision or digits past the decimal as the uncertainty. So for instance, let's say I'm adding these two numbers, 5.65 grams plus or minus 0.01 grams, 32.4 grams plus or minus 0.1 gram, and I'm wondering what that is. Well, the first thing I'm going to do is I'm going to add these two numbers together, and I'm going to round them correctly for significant figures. So I've done that. Remember, the sig fig rule for addition is same digits past the decimal as the least. So 1 past the decimal means I should have 1 past the decimal here. I should round that to 39.9. And then I'm going to add, these are absolute uncertainties, and I'm going to add them. 0.01 grams plus 0.1 gram is 0.11 grams. Generally, we're going to round our uncertainties to 1 sig fig, plus this has 1 sig fig anyway. So we're going to call that 0.1 gram. So this is my uncertainty then in adding these together is 0.1 gram. So if I was doing this in a lab and I was, for some reason in the lab I had to add up these two values, this is the value that I should write down. I should write it down exactly like that. Let's look at another example here. Let's say, for instance, I'm finding the volume of something by water displacement. So I put some water in a graduated cylinder, I put an object in there, watch the water go up, and then I got to subtract them to find the volume of this object. So I've recorded two different volumes there, and let's say my graduated cylinder's uncertainty is 0.2. Well, I'm subtracting, so I'm going to subtract those two values. I get 29.5. But whether you're adding or subtracting, you should add relative uncertainties. So 0.2 plus 0.2 is 0.4. So the way I would report my answer is 29.5 milliliters plus or minus 0.4 milliliters. And again, that's a greater relative uncertainty and absolute uncertainty than anything I actually measured. So my uncertainty goes up as I do calculations. Some people wonder why you should add these when I'm subtracting. That's the way the math works out. Would be my short answer to that question. But my second answer to that question would be it doesn't make sense to subtract them, because if you subtracted them, you would basically always get 0. So it doesn't make sense to subtract your absolute uncertainties. You always have to add them. Even when you're subtracting the main numbers here, you add absolute uncertainties. So that is addition and subtraction. There's a different technique you need to do when you do multiplying and dividing. So when multiplying and dividing, you add relative uncertainties. And then usually you want to convert those back to absolute, although you don't necessarily have to. And again, we're always going to match the digits past the decimal. And you'll see examples of where this comes up. But for instance, suppose I'm doing this. So maybe I'm finding a density. I'm doing 13.5 plus or minus 0.1 grams divided by 6.50 plus or minus 0.01 milliliters. Dividing these two, finding a density. So the first thing I'm going to do is I need to add relative uncertainties here. So these are absolute uncertainties, so I need to convert them to relative. So I need to just find the percentage. 0.1 gram divided by 13.5. That's 0.7%. So as a percentage, this number is 0.7% of this number. So that's the relative uncertainty. Same thing here. As a relative uncertainty, this is 0.2%. So my total uncertainty is going to be, in my final answer, my total uncertainty is going to be 0.9%. So I could just do the division like you normally would when finding density. I get 2.08. And I am going to convert that back. You wouldn't necessarily have to. I mean, depending on what you're trying to do, you could just say 2.08 plus or minus 0.9%. But in many cases, we're going to convert that back to an absolute. So I'm going to take 0.9% of 2.08. And what I'm doing here is it would be 0.009 times 2.08. That's how I find 0.9%. And so the way I should report this value is 2.08 grams per milliliter plus or minus 0.02. So I understand that can be confusing, definitely, especially with the multiplying and dividing. We will be doing lots of examples in class, and this is something you're going to be doing throughout this entire course, just again and again and again, and eventually with practice it will sink in. But just going to look at a couple more examples here for you to try, and then we'll go on from there. So consider the rules that we've talked about, the addition rules here. See if we can work through and figure out how this answer should be reported. Okay, so the first thing we're going to do is we're going to add them and round them for sig figs. When we're adding, the rule is digits past the decimal. So we're going to round this to 1 digit past the decimal, which turns out to be 24.1. And since we're adding, we add absolute error. So that turns out to be 0.12. But again, following just the normal sig fig rounding rules, I'm just going to round that to 0.1. So that's how I should report that value, 24.1 centimeters plus or minus 0.1 centimeter. Here's another example. Here's a division example. So again, stop a second and see how you think this value should be reported. Okay, so the first thing we want to do, you can do this in any order. We're first going to divide the two numbers just to kind of see what we get, which is 2.08, which we should round to 2.1, 2 sig figs here, 2 sig figs here. So for division, we round to least sig figs. And then we need to find the relative error. So 1 divided by 25 times 100, 0.1 divided by 12 times 100. So we're changing those in percentages. That turns out to be 4%. That turns out to be 0.8%. So that's 4.8%. Because when we're dividing, we have to add relative uncertainties. So My relative uncertainty is 4.8. Now I could round this to 5 at this point, but we're going to round it again at the end eventually. So what I need to do is, it doesn't matter too much. I need to take 4.8% of 2.1. So 2.1 times 4.8%, of course, I need to change this to a decimal form. That's going to be 0.1. So that is the value that I should end up reporting. All right, ladies and gentlemen, thanks for watching. Like I said, I know it can be tough. It can be confusing. We'll keep working on it, and we will get you there. Hope you enjoy yourselves, and have a good day.